recap, we know association rule mining is interesting and useful. We know how to compare different association rules using support and confidence, and we learned how do we calculate these two numbers as simple probabilities of the item set. Their relevant numbers were antecedent confidence, etc., ratio of the confidence, and difference of the confidence. They all can be used in finding better and better association rules out of hundreds of rules. Which ones to act on, we will use these numbers to filter and get the best ones out. But how do we actually get these rules? How do we extract? How do we convert this database into these rules? We need some technique now. The databases are not like 6 transactions like that we deal with. They are huge numbers. So first thought that comes to our mind that you may ask is, let's use a threshold. So whichever association rule is better than that threshold, we keep it. And let's use a confidence threshold. And that is quite obvious. We are going to use these two numbers, and there will be a two-step approach. First step, we are going to generate an item set from the database. Wherever the item set's support is greater than a given threshold, min support, we will keep those item sets, and from those item sets, we will generate some rules and keep high confidence rules from those all possible rules. Now, you can imagine this problem can get easily out of hand because it's computationally expensive if there are millions of transactions. For only 6 items in our database, there can be this many item sets. 2 raised to power d, where d is the number of unique items in the database. We have A, B, C, D, E, 5 items. All possible combinations of these items look like a lattice, right? So this lattice diagram let us visualize the scale of the problem that we are dealing with. How are we going to select, for example, A, D, E is better, or B is good, or A, B, C, D, E? There is an interesting rule to find out of 2 raised to power d possible item sets, which one is interesting and which one is not. But let's dig a little deeper into the numbers that we are dealing with only for this database. If we want to calculate the complexity, how many number of transactions we have? 6, right? We have 6 locations. Rangita?
Yes.
How many unique number of items we have in the database? There are 20.
20.
Total possible number of item sets that we can create with 20 items is 2 raised to power 20, which is, oh my God, is it a million? Over 1 million item sets. And in that case, the complexity of the algorithm, if we want to find the interesting ones, interesting connections in this small little database will be humongous. N multiplied by W multiplied by M operations are needed. So to the order of NMW, it's a huge problem. Even for a small database, we can see how many times the computations will run. This million multiplied by 20 multiplied by 6, around 100 million, right? Operations. So we need an algorithm, a smarter way to find the good information about the association rules. Are you with me? Do you appreciate the size of the complexity that if we do it like without an algorithm, just pick all possible items, sets, and their rule and check their support and confidence, we are going to do this NMW times. N number of transactions, W number of unique items in the database, and M is 2 raised to power unique items. It's a huge number of operations. Visually, you can see the more the number of items, the number of rules, possible rules that we can extract are exponentially increasing. For only 10 items, we need 10 raised to power 4 multiplied by 6. We can have this, we have to evaluate this many rules. So out of this, 10 item database, there may be 10 or 20 good rules that can benefit a business, but we need to evaluate tens of thousands, which is, not computationally efficient. So to reduce the complexity, number one, we need to reduce number of candidates, M, reduce number of transactions, and reduce number of comparisons. If there is a way that we can reduce these numbers, we will reduce what? The complexity. There are two options. Either we use efficient data structures, or we need to match every candidate against every transaction. No need to match if we can find efficient data structure and an algorithm. So we will reduce the complexity to a high degree. Algorithm number one is based on this principle. For all x and y, x is antecedent, y is, let's say x is an item set, y is another item set. If x is subset of y, then support for y will always be greater than support for x will be greater than support for y, if they are the subset. Visually, you can see if this particular item is infrequent, DE, then all the items that have DE in it as a member will also be infrequent. This is what the a priori principle is saying. So when you find DE to be infrequent, D is not interesting. How do you measure not interesting? Using support. The support for DE is less than the threshold that you want. In that case, all the supersets of DE, BDE, CDE, BCDE, will also be infrequent, so you don't need to check them. So you save all the operations, 1, 2, 3, 4, 5, 6 operations. You don't check them because their subset is infrequent. Their superset of DE will be uninteresting. You don't need to check based on a priori principle. So what can happen conversely? The inverse of this rule is that if something is frequent, for example, BDE is frequent, it is interesting, the support for BDE is more than the threshold, in that case, all subset of BDE will also be frequent. So you can, if you check BDE, you don't need to check BE, BD, D, E, B individually. You can just, by virtue of a priori principle, you will know that BDE support is good, so their subsets will have better support. So this a priori principle we can use into an algorithm to reduce the complexity and the number of operations we are required to perform to extract association rules. So step one, we did what? Generated item sets. We visualized them like this, like a nice lattice graph. Now, step number two, we are going to create association rules from those item sets. So both steps require a lot of computational operations, and we are trying to reduce them using a priori principle. Yes, Nishit.
So, Professor, I have a question. In order for us to use this principle, will we have to first of all calculate the
Sorry, I lost you.
Can you hear me now?
Yeah.
Yeah. So I was just asking, in order for us to use this principle, will we have to calculate the support of each item in our data?
That is what we are trying to avoid. If we want to avoid, we need to use this a priori principle. If we go ahead and check everything, then the complexity is humongous for generation of item sets, and then for checking the support and confidence of individual rules. There are so many operations to the order of NMW. So we want to reduce those, right? So first that I'm giving you is that we can use this a priori principle, which will, for example, if you know BDE, That is, if you use BDE, if it is frequent, you don't need to check BE, BD, B, D, and E, because by virtue of a priori principle, they will be more frequent than BDE. Similarly, if you are checking the support for DE and it's not interesting, DE is infrequent, then you don't need to, DE item set is infrequent, so you don't need to check BDE, CDE, all the supersets. So this is how we can reduce the number of operations using a priori principle. Everybody with me? Arushi? Rangita? Yes?
Yeah, Professor. So basically, in order to determine the frequent item set, we have to use the rule which is the support is greater than or equal to minimum support. Is that how we determine the frequent set?
Well, for support and confidence, we need to have a rule. But before having a rule, we need to generate item sets. So for generating item sets, we are trying to generate less item sets, and we use just frequency there. We use support and confidence for when we have rules, we will calculate support and confidence there. But the first step is generating the item set. Even at that point, we can come across with a huge number of things to check. Instead of checking everything, we can use a priori principle to reduce the interesting things in interesting item sets. So we can say our interesting frequency is, let's say, 50 or 10 or 100. So we want to filter out all the item sets that have less frequency than a threshold. 50, you will give that, or 2, let's say. And all the item sets, if their subset is infrequent, their supersets will be infrequent as well. If their superset is frequent, like this, BDE, then subsets will be more frequent. This is what a priori principle is saying. And we are trying to capitalize on this principle. So step 1, generation of item set, we will use a number, threshold, frequency. Any item set having frequency above this threshold is interesting. On step 2, we will generate association rules by binary division of those interesting item sets, and we will use support and confidence for those rules. Interestingly, both support and confidence and the frequency that we are using to filter out item sets, they are arbitrary numbers. So frequency can be 2 or 3, and support can be 0.5 or 0.6. Nishit? Sorry, Rangita?
Yeah, I think I'm getting it here. Okay.
Let's look at an example to apply the concept of a priori principle, and the algorithm will now look like this. First, we are trying to reduce the number of candidates. How many, let's say, transactions we have? We will look at that. All possible candidate sets that can be generated from this number will be n C1, NC2, NC3, NCN, all summed together. But we don't need to generate this many sets. If we use minimum occurrence-based filtering, the algorithm will start with 2 variables. We will say M is 2, L is 1. L is the length of the item set, and M is frequency. So while L is less than number of N is total number of items in the database, we will scan the database and create a list, which will have the frequency of each item in that list in the database. If there are no candidates in the list, we will break out of this while loop. Otherwise, we will filter all the candidate sets with less frequency than 1 and create a new candidate set of length L plus 1 from the list. Visually, same database. In the first iteration of the while loop, we scan the database. Our L is 1 here. So for every unique item, the item set length is 1. We count their frequency. So barber shops, there are 2 in the database. Convenience stores, 3. Game shop, 1. Sweets shop, 1. So we create, this is the first list that we get from the first iteration of this algorithm. Now we filter all the candidates with frequency less than 2. So M is less than 2. When we filter these, we are remained with only barber, bakery, convenience store, and fast food. In the next iteration, we will create pairs of these to create L2. Now, the length of the item set is 2. So we create pairs. For 4 items, there will be 8 pairs. So we again scan the database and calculate the frequency of each pair in the database. So barber and bakery together, they are coming at one location. And then for the next iteration, for the filtration step, we see which one of these is less than 2. We filter that out. So the interesting item sets are now bakery, convenience store, bakery and fast food, convenience and fast food. They're based on their frequency. So we keep going through this loop as long as we reach to this limit. So the number of items in the item set are equal to the total unique items. And we end up with only the interesting item sets. Then we can see the support for bakery as antecedent, convenience store as consequent. So we can then do binary division of these interesting item sets. And this simple process will reduce the number of operations to maybe 100 times less than if we don't use this algorithm. We have to do to the order of NMW complexity. So huge number of operations we need to check. But here we are reducing through this simple algorithm. This is called Apriori algorithm for discovering association rules. Now, even though it looks much better, but do you see any downside for this algorithm? For a huge database, number one, we need to generate frequent item sets. Somehow, if we can avoid this step, the algorithm or the technique will be much faster. Number two, we need to do database scans n+1 times. So if n is your length of the interesting item set, which can be 10 or 100, let's say if it's 100, you need to scan your database 101 times. Scanning the database is still not a cheap operation, right? You need to check all the database to count the frequency of the interesting item sets, which is, if it's a huge database, big data, an expensive operation still. So we will look at now another algorithm that avoids both costly database scan operations